Thank you so much, Jochen. It's a pleasure to be here, to get a chance to talk to the Developing Minds group, to share my work, and in particular to share my thinking and research about this idea that real-time interactive process drives development, and to kind of discuss how far I've gotten with that, and where I failed and where we can go on as a field. So to begin with, I want to talk about development. So development is a uncanny process in which uh, infants go from states in which really their primary communication is crying, let's say in the first month of life, to the ability at 2 or 3 years to, to use language, to talk symbolically, to use artifacts like cell phones. I think this is indeed an iPhone. Um, they're really qualitatively different creatures. And as I take it, our job is to try to explain how this occurs. And this is kind of tough. But one thing that I think we know is that development is a granular dynamic process. So we should all, take our babies to the pediatrician, and we can see how they're doing on growth charts with respect to means and these smooth curves. But these smooth curves are not how children actually develop. If we kind of zoom in the microscope, and I'm going to kind of play with a bunch of metaphors here, but here are the metaphors of microscope. So we're kind of looking in at one child's growth curve. We see in the realm of physical development, thanks to the work of Lampel, who was a physical anthropologist, and she showed here it's, I think, with the length of the baby, but it's also true of head circumference. It's really true of every developmental parameter that she looked at. We see saltatory growth. So that means that babies' physical growth occurs in spurts and little jumps. These are these little more vertical lines here, and these are interspersed with periods of relative stasis. And all the growth that babies do happens during these jumps. So we know, but I'm just reinforcing that it's not a question of small curves. It's a question of um, quick movements forward and periods of relative stasis. And I'd like to get into that more with the fanciest of technological sensing that you'll ever see, which is a description of this process in prose by Piaget. So Piaget is talking about his son Laurent at 16 months. There's a piece of bread in front of him, and there's a stick. And thanks to modern AI, we have a photograph of Laurent at his table, totally made up by AI. Um, and what happens is, what he likes to do is he likes to reach for the bread with his hand. But Piaget kind of puts the stick like between his hand and the bread, and he says that it's very visually suggestive. So what does Laurent do? He grabs the stick, but he grabs it towards the middle of the stick. So no success, and he recommences like any good biological agent to try to reach it with his hand. And I want to emphasize this because um, if real-time interactive processes constitute development at a larger time scale, real-time interactive processes are messy. They go up and down like Lampel's growth, and it's just not a continuous linear process. Okay, so he fails in reaching towards the piece of bread, but then he grabs the stick. Piaget says accident or intention, and he pushes the bread around, and then he kind of is able to draw the bread towards him, and he does this twice. So in Piaget's mind, and I have to say I'm convinced, what we've seen, what he saw, was the development of means ends behavior, using one thing to get another, the cunning of reason, like this big old not human specific, but we used to think it was human specific cognitive achievement. And how is it happening? It's happening in real time, subject to the vicissitudes of like how big the stick is and where you grab it and its angle. So that's the kind of uh, uh, ensemble of temporal levels that I'm interested in talking to you about this relationship between real-time interaction and development. And I'm going to do it in three, portions that kind of intermix. The first is emotion and interaction dynamics. And like Johan said, I'll also talk to you about, cool things that we found about emotion and interaction using sensing devices as I move along. I'll then talk about autism and attachment and, processes that we've seen there, including some kind of sensorization of the measurement of attachment. And then I'll talk about our work in the preschools, interactive behavior in schools, the IBIS project. Okay, so we're going to get going, and we're going to get going in terms of my work, not Piaget's work, with neonatal smiles. So this is work with Marco Dondi, and it's a great kind of dynamic systems developmental cascade illustration in which infants in the first month of life will show very mature smiles. They involve eye constriction, which is this a feature of smiling that I'll talk about later. But babies do this when they're asleep and in drowsy periods. So like this, we're interested in the emergence of the social smile here. They've got the smile, but they don't have the social. They're asleep. In the first month of life, first month and a half, depends on the baby, they get better and better at attentive states. They're awake for more and more time. They focus. They can corrugate their corrugator, and they can furrow their brow and look at the person, but they are not smiling. So the only point that I'm trying to make here is that when babies put these two things together, this attentive brow, maybe in the service of recognition, together with a muscular pattern of smiling, this is the developmental achievement of the social smile. And they're doing this in a particular moment, in a particular instance. I put this image here. I said I play with metaphors. So this, I admit this is an AI generated image also, but there are only two. It was Piaget's son in this one. That's it. But it shows us, it's an illustration of a thought experiment, which I think is kind of self-evident, that if we think, oh, this development occurred on the level of months, a month or two. But it could be years. Months are composed of weeks. Weeks are composed of days. Days are composed of hours and minutes and seconds and so on. It is one continuous temporal flow. So I think that's really the essence of what I'm going to be saying here today. But I'm going to say it in some cool ways. So here we're looking at the development of smiling in the first 6 months of life. So, all of this is social smiling. It's happening in face-to-face interaction. It looks like this. This is video from my dissertation. The baby has a big old smile. You can't see it very well, but she has some eye constriction going around, the Duchenne marker. Her mouth is open. That's practically invisible. She's looking at her mom. Her mom is smiling. And during periods when these engaging periods, when the baby is looking at the mom and the mom is smiling, this kind of affectively intense smile, eye constriction and mouth opening, tends to predominate. It tends to increasingly kind of displace other smiles in this particular context. So the social context is shaping the ability, the development of baby's capacity. And we're seeing this in real time here, and then in this small sample of 13 babies, but observed weekly here. So Smiling too occurs in the smiles that occur in real time. This developmental, these interactive processes are constituting that development. And let's watch what happens next. So this is a marvelous achievement. Ayana, that's the baby, was watching her mom smiling, and she turned away from her and she kept smiling. So as biological humans, we're like, yes, of course, she kept smiling. But it's not so simple. Um, it turns out that if you look at 3-month-olds and you look at that pattern, so this might be hard to see, but looking, gazing, beginning to smile, and then stopping the gaze but continuing to smile, that just doesn't happen at 3 months. 3 months old, they smile, but they smile within an envelope of gazing at the parent's face. So in other words, we're looking at, we're microcoding here. We're looking at the temporal patterning, precise temporal patterning of behaviors. There's a randomization behind this, so we're looking at z-scores, but we're looking at the temporal succession of behaviors. And we're looking at them in that fine detail because these are constituting larger developmental processes. Here, this is showing that babies, this is the envelope period in which the smile is encased within the gaze at 3 months. That becomes much less predominant at 6 months. At 6 months, what babies do is they gaze, they smile, they stop gazing and stop smiling, perhaps in the service of emotion regulation. And actually, if you put the two parts together, and here we're looking at, these are unpublished data from the dissertation showing this pattern going continuously in time. It's neat that babies become more likely to become intensely positive during these engaging, arousing, interactive situations at the same time as they become more likely to disengage from those situations in the course of them, perhaps to regulate their own emotion. Okay, so that was a bunch of what I'm trying to illustrate in terms of the coincidence of real-time processes and developmental processes. And now I'd like to tell you a little bit about different kinds of affective expressions, and then we'll again relate it to both to interaction and to development. Okay, so my fellow scientists, this is behavior. So these are smiles, and as the image goes from left to right, the smiles increase in intensity. So that's kind of the level. It's kind of the more mouth-centered actions. These are cry faces, the prototypical facial expression of negative affect, and they also increase intensity as risorius, the muscle that pulls the lip corner straight back, is contracting more and more. So we tend to think of things like smiles and negative facial expressions as kind of modular top-down entities. What I'm going to argue is that they have common building blocks. So this was originally an idea of Darwin's, that eye constriction becomes stronger and stronger as the facial expression becomes strong, as the smile becomes stronger and stronger, and eye constriction, more or less the same eye constriction, becomes stronger and stronger as the cry face is more intense. And sorry, I'm moving my watch on top of the laptop. So we illustrated this in 2 ways. So the first was using computer vision. So here we're using these somewhat overtrained support vector regression models, and they're outputting the intensity of the smile, the eye constriction, and so on. So we have kind of baseline objective measurements here. And then we use this joystick. I'll talk more about it later, but basically there are ratings of how positive and negative the full video is when people perceive it. The finding is that when there's a smile, if there's more eye constriction, it's perceived as more positive. So you might think, oh, more eye constriction, more positive. But no, if there's a cry face, then if there's more eye constriction, it's perceived as more negative. So the argument here is that this is a fundamental grammar of early emotion expression in which eye constriction increases the intensity of affective valence. Here it's a perceived affective valence. Here it's situational. There's an experiment going on, but to show you the experiment, I'm going to show you a kind of more modern version of the work. This is the work of Atira Ertugrul. She developed the computer vision here. She's at Utrecht. So these are her models in which you can see that we're measuring these action units from a model of the baby's face taken from the video. That was the smile. This is the cry face. And we're interested in these Duchenne expressions, which a Duchenne expression just means that it involves a certain level of eye constriction. And we find something that I find provocative. Okay, I'll stop them playing, which is that face-to-face still face effects. And I think we're all familiar with that, but this is here they're playing. Here, the parent adopts a still face, and here they re-engage in interaction. Infant Duchenne smiling is creating this pattern, which is the prototypical face-to-face still face pattern. Non-Duchenne smiling, not so much. And this is all from computer vision. If you look at cry faces, infant cry faces are what really climb in the still face and climb in the reunion as well. And it's also true for moms. So the mom pattern of more positive affect in the face-to-face, a decline because she's supposed to be holding a still face in the still face episode, and then re-uptick in the re-engagement. This is driven by Duchenne smiling more so than by non-Duchenne smiling. So super. And then I think I repeated this slide, so bear with me for a sec. Okay, so now what we're going to do is we're going to take these kind of findings, if you will, about Duchenne smiling, and we're going to use them to look at face-to-face interaction. So I said we'd get back to interaction, so we're getting back to interaction. So here, we have kind of a level in blue of the baby Duchenne smiling. So there's a little blue dot here. So not much smiling going on the baby's part, some smiling going on in the mom and the red's part, and then we can see how they interact. So I couldn't quite catch who led it, but they're both now smiling a bit more. I think they're up about here, and I think the mom's going to keep going up, but the baby's going to kind of decrease their smiling first and drive the dyad down right here. And then everybody's stopping and the baby smiles more, maybe in response to the mom tickling. And when the baby does that, that drives the mom smiling up. So you can see these, well, really interactive process. And I have to say, this is a 2009 paper. And I know I'm getting old because now I sometimes feel like there were things that were captured in particular papers that, you know, that I would like to capture again, essentially. But with respect to our larger principles of development and so on, let me stop them. This was a 2-dyad paper. This is the time series that you just saw. This is like I'm not sure if it's peak picking, but it's peak identification. So there are these red periods are periods of high local correlation in the intensity of mother and baby smiling. And you can see that things go up and down. So, it's not a continuous interactive process of high alignment or high responsivity. Instead, things change in time. And this is a bit of a call. We investigated this further with this. Remember, I was talking about that joystick interface. So here's what it looks like. So a bunch of individual observers, undergraduates often, come in and rate the baby from positive to negative. Then we aggregate their time series into an aggregate time series, a mean time series of the infant, of the parent in blue, infant in green. And our time series analyses show that the association of parent affect on the infant itself changes in time. So these lines, some are in green, some are in black. We don't have to pay attention to that. But the level of influence, or the level of association itself, the level of association itself changes over time. So this is important because we often think of interactive parameters like responsivity. And we take a mean measure and we say, well, how is this related to, later language development or later attachment? But it's important to remember that that mean level over the course of an interaction itself was composed of more micro variations in responsivity, and doing something like looking at that variability or that variability in time, these may better capture actual interactive processes, and so better capture actual developmental processes than may mean levels. And I'm going to try to illustrate that here. I should have kind of captured a little image of the mom and baby there, and to remind us of what the actual interaction looked like. But this is us looking at that continuous process in a more discrete fashion, in which we're just looking at the onset and offset of infant and mom smiles. And there can be kind of two things that can happen. There can be no turn taking. So if mom begins a smile and then ends a smile, there was no turn taking because the baby didn't have a turn. Let's say the baby's not smiling. By contrast, if the infant starts a smile and then the mom starts a smile, a pattern that we in fact saw, that's one turn. If the mom starts a smile and the infant stops a smile, second turn, because it's the next partner who acted. And that kind of smile turn taking increases with age. So I consider this this is an important finding, at least for me, that I guess really the level of responsivity of both partners increased between 1 and 6 months. And I'm not going to get into it a lot, but I think it's important for us to remember that each of these turns or not turns is itself composed of, a probability density function in a given state. Let's say nobody's smiling, the infant last stops smiling, what's going to happen next? And what it shows actually is that there's a tendency for the partner who acted most recently to act again. So there's a tendency for no turn taking to happen. So our ability to take turns early in life, the ability of the dyad to take turns, is something of an achievement here. So this is the likelihood, if neither is smiling and the infant stops smiling most recently, the likelihood, you can see this temporal pattern in which at first it's very unlikely in the first milliseconds after a behavior for anything to happen, and then there's that kind of nice curve. So this is what things look like in a more continuous way. But again, big picture, and I think full of possibilities. we have sequences like this, right? Of infant smiles, mom smiles, and so on. Smiles and no smiling. And these have durations, right? So a cool thing we can do is use machine learning, in this case, inverse optimal control approach, not to measure the smiles in this case, but well, to measure and infer from the interaction, to take the sequence of changes and to ask, given the data, given that infants tend to smile for this duration in this state, and this tends to occur, what happens is that mothers tend to smile. We can infer there's a posterior probability of what each partner was trying to get out of the interaction, of the states they were trying to achieve. So, what do mothers want? Mothers want what I think we would imagine. They want to increase states of mutual smiling. Very provocatively, this is not what babies appear to want. Babies appear to act so as to attain, and I'm not arguing that it's conscious or anything, just that these are the posterior probabilities, to attain states in which the mother is smiling and they themselves are not smiling. They try to maximize smiling in. This might be part of a larger process. So I think it's part of the larger process that we saw of they smile at the mom and then look away and stop smiling. So they're interested in kind of regulating their emotion in this temporal fashion. But this is, if you just look at the states that it appears that they're trying to achieve, it was something of a surprise to me, and I think quite interesting. So our friend Piaget said something that stuck with me, which is, if you kind of want to understand a developing agent, you have to understand what they want. So Piaget said, it's not really all about, the cognitive abilities with which they can achieve things. So, they can use means to ends and so on. It's also what the agent desires. So I think it would be cool to use inverse optimal control more. And I think it's being used, although maybe conceptually the same, but maybe under different computational instantations, to understand what kids want at various ages. And as well, we might use it to try to ask whether, as Jochen was intimating in my own work, do kids who are developing autism, do they act so as to attain different things, let's say in face-to-face interaction or in later interaction? And I'll get to that in a second. First, though, I want to bring us back to our developmental story. I want to do it in a conceptual way, and I want to do it through the still face. So this is the idea of a dynamic still face effect. So the parent and infant interacted, they played, the parent then adopts the still face. This is, an image showing the still face. So what's the baby going to do? And I'm going to, this video hangs up, and sometimes it hangs up the whole PowerPoint, but I'm going to give it a try. So this is the beginning. So in the beginning, Michael Goldstein has great data on this, showing showing this curve of kind of, and with vocalizations of trying to get the parents, presumably trying to get the parents' attention. At the beginning of the still face, he shows that it's related to prior parental responsivity. But what you can see here is that the infant tries for a bunch in terms of like gazing at the parent, but then, they become occupied with other things. It's not working, presumably. We could talk more about that, to get the parents' attention. So they look away more and more. They do this with a bunch of social behaviors. Their cry faces go up, their smiles go down. I'm going to focus on a logarithmic decline in gazing at the parent during the still face, because it turns out that this is related to later attachment in a conceptually interesting way. So infants whose decline in gazing is kind of at a Goldilocks, not too much, not too little level, end up showing secure attachment. Infants who respond to the still face by a steep decline in looking go on to show an avoidant attachment. So that means, and we'll look at attachment next. In the strange situation, once there's no ability to interact with the parent, or in the strange situation, following an inability to interact with the parent, they tend to ignore the parent. So if there's evidence of non-responsivity, they slow down their social behaviors drop really quite precipitously. By contrast, resistant infants, infants who will go on to be resistant, so what they show is they just don't show this decline, right? So the slope it's near zero. It's not negative. They keep gazing at the parent over the course of the still face. They keep trying to get the social behavior that's presumably not forthcoming. And in the strange situation, they keep up mostly negative affective behaviors after the parent returns and trying to get them to engage again. So I think this is a neat kind of illustration of conceptual isomorphism between social behaviors in the still face and in attachment, showing this, I hope, underlying development of this pattern of when you use social behaviors to engage with a parent who's less than responsive. Okay, we get to see him again. And as we noted, we can also look at this to look at autism outcomes, and ideally to understand something about the development of autism, although we might save that for the discussion. So here we're looking at baby siblings who are the younger brothers and sisters of a child. They have an older brother or sister with autism. So about 1 in 5 of the baby siblings will themselves develop ASD, autism spectrum disorder. So it's kind of a big deal to understand, particularly among the baby siblings, who will and who won't develop ASD. And here we're looking at the face-to-face still face, but we're looking from the face-to-face to the reunion. Now, I guess in the last slide, we focused on the still face. Here we're looking at the face-to-face to reunion. So low-risk kids show this decline that we also saw in the Duchenne paper. Kids with ASD in red show low levels of smiling to begin with in the face-to-face and no effect after the still face. The level is the same. So this is a kind of intriguing finding. And we'll get back to it in discussing attachment in autism. And to prepare for that, I just want to show you the strange situation, which is used to assess attachment, but here we're trying to get at it with kind of more objective measures. So these are connects, these are old connects. And this is the distance between the baby and the mom who are being continuously tracked. This is just one view of them. This is a representation of them. So here the baby is crawling towards the mom, so the distance between their two kind of head boxes declines. The results of this particular study showed that if you really look granularly at this assessment, you can show that there's an effect of both partners on ratings of the infant attachment interaction. So I thought that was important. That was the stranger leaving the room. The baby crawls towards her. As he does, the distance of the baby to the mom increased. And if we wait long enough, the baby will then crawl to the mom again. It's a nice, it's the same pattern all over again. So a way of looking, again, granularly at behavior to discover, I think, what should be evident, which is if you put two people together, they're going to influence each other's behavior. I think that should be our premise. And we've explored that in a bunch of other work, including the still face, which turns out not to always be quite so still, that we could discuss. So here indeed, the baby, I think, crawled toward the mom and is now crawling away to explore. So that was our look at attachment. We look at that again with in the context of autism. I should have put another red arrow right about there. So these are low-risk kids who they have an older brother or sister who didn't have autism, but these are baby siblings. High risk is what they're labeled here. So these are baby siblings who did not themselves develop ASD. Most of them had secure attachment. A few of them had insecure attachment. These are our high-risk siblings who did have ASD. More than 50% had insecure attachment. And this tended to be resistant attachment. And this research surely needs to be replicated, but I think shows that, you know, this is a potential biomarker, but in the socio-emotional realm of future ASD among kids and only among kids who have an elevated likelihood of ASD. Okay. With that, I want to save some room to talk about, to ask whether this confluence of interactive process and developmental process is also true at older ages. And at older ages, kids are often in groups in preschools, about half of the kids in the States. And preschools are complex processes. So this is a video that you're watching from the net, in which is focused on this girl, and she feeds the baby, and then she has a pretend lunch with a friend. And we can learn quite a lot about her by focusing on her. But everybody else is also having their experiences. So sometimes this kid is here, sometimes he goes to get a doll. There are other kids walking back and forth. Some kids are driving cars back and forth. This guy is actually walking back and forth on stilts. It's like that, you know, that gorilla movie in Introductory Psychology. There are no gorillas, I don't think, but you get the point. Everybody, there are lots of kids having lots of experiences. So we try to get that through these instrumented vests. The acronym IBIS is the name of a bird. The bird is wearing a vest. They have these position trackers, so we know every, you know, dot is a kid. The little arrows show which way they're facing, and then I'll tell you when they're the big arrows, they're speaking. And I think I'm running a little low on time, so I'll move on, but we'll be talking about the audio, and I'm going to give you a very brief review of our work here. So this is work in which we began just with the sensors. So we're only looking at movement. This is a classroom in Germany, 5-year-olds, and the kids in red are girls and the kids in blue are boys. And we have all these colored balls moving around. We want to know when they're in social contact. Like, are these kids in social contact? Well, kind of looks like it. They're kind of close. Are these kids? It's hard to know. So we infer social contact based on kids being in distances where it's greater than chance that we observe that distance, given all the possible distances that exist between all the kids over the entire space of the observation. So this is called the radial distribution function. Comes from computational physics. It can be applied like to molecules in a gas, in a liquid, and in a solid. And if we have time, we can talk a little bit about that. But here we're just inferring social contact. We're doing it only on the basis of distance. We made a nice network. We discovered some things about kids' distribution of social contacts with more and less preferred partners. But we also decided that we would like them to say they were in social contact. We wanted them to be within 45 degrees of face-to-face. So that's what's going on here. And that's why these kids are triangles. And I don't know what will happen here, but like these two kids, I think, are in social contact, the two red triangles. That is, they're within 45 degrees of an imaginary line connecting them in terms of their interpersonal orientation. So this is another way to get at social contact. Social contact has been important conceptually for us. So on this side of the graph, we're looking at we're looking at homophily between kids, TD kids, typical development, DD, a developmental disability that's not autism, and then as Jochen was saying, ASD, so kids with autism spectrum disorder. They tend to hang out with each other, with kids in the same group. Levels of social contact are higher than they are in kids, pairs formed by kids from different groups like TD-DD. So again, TD-TD here and then different groups here. Okay, so this is the process of homophily, and then looked at, this just got accepted at Autism Research, looked at a little bit more broadly. It is striking that typically developing kids prefer, based on social contact, also velocity, which I'm not showing here, prefer to be in contact with peers, but kids with ASD prefer peers and teachers equally. So just some cool stuff we can do with social contact. Okay, now let's gear up to introduce vocalizations, and from there we'll move back to the level of development. So we find this dyadic process running through the classrooms that we've looked at, in which over monthly observations, the degree, where degree really is the rate of vocalization onsets per hour, the degree that A speaks to B predicts how much B speaks to A in the next observation, like let's say a month into the future. We're controlling for various autoregressive factors. And of course, A and B are kind of made up. So the degree to which B speaks to A, in turn predicts the degree to which A speaks to B in the next observation. And this is true overall, this is true for all pairs in the classroom. So we see, right, this group of people, of kids milling about, some are on stilts, but there are dyadic relationships in there. And they seem to be accounting for a fair amount of the variance in classroom speech. This is an illustration. So this is, if you will, A's speech to B, or for all A's and all B's, in one observation is associated with the rate of B's speech to A in the next observation. And now, crucially, these are, if not real time, these are processes that occur over the course of a school day. So each dot is a school day. But you can also say, how much do peers speak to the target kids in the fall? How much A to B in the fall? That predicts how much B to A, again, for all A's and all B's in the spring. And that, in turn, is associated with assessed language ability. So these presumed real-in-time interactive conversations are driving speech over the course of the year and associated with assessments of language ability. The same is true. There's a dissertation that follows this, so I'll kind of talk a little bit about those results as I talk about this. The same is true for teachers, in that the phonemic diversity, the number of speech sounds in each utterance of the adults, is associated with that of the kids. In general, there's kids with typical hearing have more phonemic diversity than do kids with hearing impairment, even though the kids with hearing impairment have augmented hearing devices. But you can see this kind of in-time association between hear and phonemic complexity. Again, teacher phonemic complexity predicts kid phonemic complexity, fall to spring, illustrated here, and end illustrated here. It's associated with both expressive and receptive language skills. Super. So this is our kind of work with vocalizations and with those Lena recorders. But of course, some of the time, the kids are saying things. So this is where I think it would be best to this is where the cup flicker. So I want to play you a little bit of so if we use these Sony recorders, we developed a pipeline to identify whether it's a teacher or child who's speaking. And we're currently using Alice, but or in these data we're using Alice, but there are more sophisticated methods now. And then we're using Whisper to transcribe their vocalizations. Classrooms are extremely noisy, a lot of overlapping voices, but sometimes you can hear stuff like this, and just raise your hand if you can't hear it. And so this is the Whisper transcription and an expert transcription. So they go on. So some of the time we can really get a sense of kind of the words that are being said, and there are various metrics here on the right. The words that are being said, you can also hear when the expert and Whisper, differ, and you might have heard something different than I sometimes hear something different from both Whisper and the expert. Importantly, I hadn't thought about this before. The length of the utterances, this is going to be important. It's going to be important because mean length of utterance is this great measure of kids' language development and kids' actual language production, right? We're interested in behavioral development. We want kids to do things. But to get child MLU, traditionally, you have to devise a assessment that's not much of an assessment, an observation, and then code it by hand, and it's going to take a while. So the idea is that this can take less time, and we find that there's a strong association between the kid MLU and their language scores on the PLS, the expressive and receptive, and you can also see these big effects for kids with hearing loss have lower MLUs and lower assessed language, and kids with typical hearing do better on both. But, right, those are just language assessments. What's cool is to ask about the development of each individual. So these are 2 classrooms, preliminary data, not published. 2 classrooms, 2 observations of a single classroom. So 2 years of observations of a single classroom of these kids. And particularly for typically hearing kids, MLU goes up with time, not a lot, but it's statistically very clear. And it's messy, right? It's as messy as Laurent Piaget's son, he reaches for it, he drops it, he doesn't drop it, but he goes back to reaching it for his hands. Kid MLU is going up and down on different observations. But as it does so, it grows month to month. Teacher MLU is associated with the development of child MLU. And for teacher MLU, what I take to be happening, but have not shown, but what I take to be happening is that this is the teacher MLU heard by the child from the child's recorder. That what we're getting is some kind of linguistic interaction. Based on that premise, teacher MLU, so mean teacher MLU over all the observations, is associated with the slope of the increase of child MLU. And this appears to be particularly the case for kids with hearing loss. And you can see, right, these are tiny numbers because MLU is in some ways very stable, but it is changing over time and the differences between kids are meaningful. And then we also did it in that kind of that other way in which we look at mean teacher MLU in the fall, which is associated, again, particularly for the kids with hearing loss, with the child MLU in the spring. So coming kind of full circle using these computational methods of sensors in the group setting of the classroom, so in real life, to try to understand links between interaction and development. That's what we are doing here. Again, this is our thought experiment showing that, years are composed of seconds and so on. I think this is self-evident, but worth worth noting and really thinking about. Um, and we did that, and throughout, I was using this idea of behavior imaging, which comes from Jim Ray, which is really let's take behavior and its quantification seriously the same way we take the behavior of the brain seriously in neuroimaging. Let's take behavior seriously. We looked at correspondences between real-time interaction and development in the development of intense smiles and the kind of emotion regulation pattern of disengaging from gazing at the parent's face while smiling. We looked at it in terms of autism and attachment, and in particular, for example, that isomorphism between social behaviors in the still face and in attachment, and seeing that developmental progression. And then we just did the same in the school interaction, in which I think both at the level of vocalizations, but then at the level of verbalizations, we're trying to show that these interchanges are contributing and are part of language development. So having said that, two things that I very much want to mention. So first, a big thank you to, all the babies and children and parents and now teachers and school administrators who make this research possible, to our funders who make this research possible. And then you can imagine the number of research assistants involved in all these projects. Here's our current lab, and that lab, so the IBIS stuff that I showed is co-directed by myself and Lynn Perry. And it really takes a team of us to make these things happen. So thanks to all of them. Thanks to you guys. And before I ask for questions, I know it's here, a reminder that there is, this is a computational group, and a reminder that there is this call for papers, a special issue or a special collection of topical papers, computational approaches to understanding development. And Ori Osmi is also will be a co-editor of that. And yes, if you send us, if you submit earlier than the deadline, there's a submission deadline of the 1st of February. But if you submit earlier than the deadline, we can start getting things out for review earlier as well. So thanks.